across the vast ocean of the cosmos, where starlight falls quietly like ancient grains of memory. There exist pockets of darkness so dense it feels as though even silence itself is being crushed. People call them black holes. Silent beings that bend space, twist time, and whisper to humanity. Reality is not as simple as you think. In their presence, physics softens like flowing water. Light trembles like a frightened child, and our very existence becomes a delicate question. If you cherish journeys that both lull you into rest and awaken your curiosity, gently touch the like and subscribe buttons. So this voyage always has you as a companion. Thank you. Truly. So then, what is this darkness after all? What is a black hole and how is it formed? In the quiet vastness of the cosmos, where starlight drifts like fading memories, there are places so dense and silent that even the prime universe seems to hold its breath. These dark regions, the black holes, are not simply astronomical objects, but the final whispers of stars that once burned with unimaginable brilliance. To understand them is to understand a cycle older than galaxies. A story in which creation and destruction hold hands. And so begins the journey, often described as black hole physics explained. A path where science softens into poetry, and the universe reveals its secret rhythms. Physicist John Wheeler once said, "A star is born from gravity and dies into gravity." The life of a massive star follows this truth with a kind of cosmic dignity. For millions of years it balances pressure and pull, fusing lighter elements into heavier ones, shining because its own collapse is kept at bay. But even stars have endings, and theirs begins softly, almost imperceptibly. As hydrogen fades, the core turns to helium, then carbon, then neon and oxygen, each fusion cycle burning hotter, faster, more desperate. A star aging is like a tired traveler climbing the last steps of a long staircase, reaching for breaths that come heavier each time. But when it begins to forge iron, its fate is sealed. Iron neither releases energy when it forms nor when it breaks apart, leaving the core without its only defense. Neil deGrasse Tyson captured it perfectly. Iron is the ash of stellar nuclear fires. Gravity, always patient, finally wins. It crushes the core inward, collapsing matter with a force so intense that temperature and pressure rise beyond comprehension. The outer layers crash inward and rebound in a spectacular explosion. The supernova, a single moment bright enough to outshine entire galaxies. Carl Sagan reminded us of the beauty hidden in this violence. We are made of star stuff, all the gold, silver, and heavy elements that shape. Planets and people are born from this one furious instant. What remains after that brilliance fades depends entirely on the weight of the core left behind. If that remnant is modest, though modest, still means more massive than our sun, it settles into a neutron star. A city-sized sphere where matter is pressed so tightly that a teaspoon would outweigh mountains. But if the core is heavier still, no force can resist further collapse. Atoms fall apart. Neutrons give way. And matter continues its descent into something no equation fully captures. Roger Penrose once reflected on this process. The formation of singularities is the triumph of gravity. And so the singularity forms, the heart of a black hole, a place where space-time curves so sharply that nothing, not even light, can escape. Around it lies the event horizon, the boundary between what can be known and what is forever concealed, beyond that frontier, our familiar understanding dissolves, and time itself becomes a shape that bends back upon itself. The death of a star is therefore not a final extinguishing but a transformation. Its outer layers scatter into space to seed new worlds, while its core contracts into a shadow that warps the geometry of the universe. In that strange duality lies a quiet lesson. Collapse does not always mean destruction. Sometimes it is the beginning of a new form of existence. The universe has shown us repeatedly that endings are simply gateways wearing darker clothing. When I reflect on this, I am reminded that humans too live by cycles we cannot always see. Moments when we feel crushed, overwhelmed, or stripped of our own light may simply be the gravitational stages of growth. Even stars must implode before scattering the elements of life. Even darkness can create futures it will never witness. Black holes teach humility. They remind us that reality is layered with mysteries we may never entirely understand. And yet, as physicist Steven Weinberg wrote, the more the universe seems comprehensible, the more it also seems pointless. It is precisely this tension, the known and the unknowable, that makes the cosmos feel alive. We exist in a universe where light can be swallowed, where time can slow to stillness, where a dying star becomes the most powerful object imaginable. Perhaps that is why learning about black holes feels strangely meditative. Their story is not only an explanation of physics, but an invitation to breathe with the universe, to understand that destruction and creation are threads of the same tapestry, to realize that our existence, fragile as it is made from the ashes of stars that dared to collapse. And so when you gaze into the night sky, remember that somewhere out there, a massive star is taking its final breath, folding into itself, becoming the next chapter in the long cosmic poem we all belong to. In the quiet corridors of the cosmos, where darkness moves with the softness of velvet, there exists a place where reality bends more deeply than anywhere else, a place where light loses its courage, where time forgets its rhythm, and where the universe whispers its strangest secrets. Among all strange space phenomena, the black hole stands alone, not simply as an object, but as a boundary between the known and the unknowable. To understand it is to stand at the edge of understanding itself. Listening to the faint breathing of space-time, the first truth we must accept is this: we never actually see a black hole. What our telescopes reveal is not the creature but its shadow, the limit where light gives up. What we call an image of a black hole is actually the glowing ring of tortured photons circling the event horizon, the last place where light can still make a choice. Stephen Hawking once said, "Black holes are where God divided by zero." And in that strange humor lies a deeper message that our senses are never granted access to the truth behind that darkness. We only see the horizon, never the heart, never the thing itself. That boundary, the event horizon, is the most misunderstood feature of a black hole. Many imagine it as a physical surface, a wall of some kind. But in truth, it is only a threshold, a mathematical condition where escape becomes impossible. Not because of a force pressing outward, but because the inward pull has overwhelmed every path a particle could take. To cross the horizon is simply to pass a point of no return, a point where every future is directed inward. But what lies inside that fall? Inside the chamber of absolute gravity? For decades, physicists have wrestled with the concept of the singularity, a point of infinite density and zero volume, a place where all equations tear open and the universe stops behaving like anything we recognize. A region where the curvature becomes so strong that no physical theory can continue to describe it. Perhaps it is truly a point. Perhaps a ring. Perhaps something stranger still. But whatever its form, it is sealed away from us by nature's strongest curtain. This is why no one can know what waits inside the horizon. It is not a limit of technology, but of logic itself. No information can escape. Not a photon. Not a particle. Not a story. Einstein once warned, "The distinction between past, present, and future is only a stubbornly persistent illusion." Inside a black hole, that illusion collapses completely. Space falls, time stretches, causality unties itself like a ribbon left in the wind. This leads us to one of the most breathtaking ideas in all of relativity, the slowing of time near a black hole. To the traveler falling inward, everything feels strangely normal, almost peaceful. But to an outside observer, that same traveler appears to slow, fade, dim, and freeze just above the horizon. Not because they truly stop, but because time itself stretches endlessly as gravity deepens. Carlo Rovelli described it beautifully. Time is not a river, it is a landscape, near a black hole. That landscape becomes almost vertical, climbing it becomes impossible. Imagine watching a friend fall toward the horizon. Their movements grow slower, their voice grows faint, their image reddens, then disappears. To you, they never cross the horizon at all. They are frozen on its edge, suspended in a moment that stretches toward eternity. This is not illusion, it is physics speaking gently but firmly, telling us that time is not universal, that each clock in the universe writes its own autobiography. Yet from the traveler's point of view, nothing unusual happens. They move forward, step by step, into the dark. They cross the horizon without resistance. Because the horizon is not a wall. It is only a place where every future points inward. From their perspective, the outside universe suddenly races forward. Stars age and die in an instant. Galaxies drift like sparks on water. And time becomes a river pouring only one way. This duality, two realities true at the same time, is one of the most haunting features of general relativity. It invites us to question not only physics, but our own certainty about the world. If two observers can witness the same event and see completely different stories, then what is real becomes a more delicate concept. As Kip Thorne once wrote, "The universe is under no obligation to present itself in a way that is easy for us to understand. There's something deeply human about that. We too live inside horizons of our own making, boundaries of perception, belief, and memory. We see only the shadows of people's stories, not their singularities. We watch events unfold from the outside, unaware of the time stretching that occurs inside another person's life. Sometimes we think someone has stopped moving, when they are simply caught in gravity we cannot feel. And sometimes, like matter falling toward a black hole, people slip into new versions of themselves while we still see them frozen in an older moment. For me, that is the quiet wisdom hidden inside this cosmic mystery. The event horizon teaches humility. It teaches patience. It teaches that what we see is never the whole story, that realities can coexist, that endings may not be where they appear, just as matter never truly disappears but becomes part of a deeper curvature. Our own transitions carry us into unseen chapters. Black holes may be the darkest objects in existence, yet they illuminate one truth with startling clarity: that the universe is far stranger, more subtle, and more beautiful than our habits of thought allow. And in that strangeness we find perspective, we find wonder, we find a reminder that mystery is not the enemy of understanding, but the doorway to it. As you continue this journey, let these ideas settle gently like stardust. Let the strangeness of space-time soothe you rather than frighten you. For in learning to see the universe with softer eyes, we also learn to see ourselves with more compassion. In the quiet fabric of the cosmos, where starlight drifts like ancient breath, one of the most mysterious stories ever observed begins with a whisper of invisible radiation from the direction of Cygnus. It was subtle, almost shy, and yet powerful enough to rewrite our understanding of the universe. This faint tremor in the X-ray sky became known as Cygnus X1, a place where the darkness reveals itself not with light, but with the energy of matter being torn apart at the edge of an unseen abyss. In the study of quantum gravity and black holes, this was the first time theory reached out and touched reality. Astronomers were puzzled when the X-rays arrived, for there was no visible star shining at that spot, no warm glow, no flicker, only a silent blaze in the high-energy spectrum. It was as if something were burning fiercely yet refusing to show its face. Stephen Hawking once admitted, "Observations of Cygnus X1 convinced me that black holes are real." For him, caution incarnate. This was a revelation as profound as a sunrise in the dark. Why does a source that screams in X-rays yet hides in visible light lead us toward the idea of a black hole? Because only a place of extreme gravity can heat in falling matter to millions of degrees while swallowing all softer light. Around such an object, matter spirals inward, rubbing against itself until it glows blue and white in the X-ray spectrum. Yet before it can emit a single comfortable photon of starlight, gravity steals it away. It is a cry of energy at the threshold of oblivion, but the universe left another clue, even more poetic. Beside the invisible object was a bright, massive star, drifting in a perfect orbit around something that refused to shine. By watching its path, its wobble, its elegant sweep through space, astronomers could weigh the darkness it danced with. The mass turned out to be far too great for a neutron star, far too heavy for any known compact object. Only a black hole could be its partner. Einstein once wrote, "Gravity is not a force, but a curvature of space-time." And in the orbit of that luminous companion, we saw the curvature of an invisible valley carved by an object that could not be seen nor touched nor illuminated, reality bent around a shadow. What makes this discovery even more enchanting is not only what it says about Cygnus X1, but what it hints about the deepest parts of physics. If black holes exist, their singularities might exist. And if singularities exist, then general relativity is merely half a story waiting for a partner. Quantum mechanics whispers one truth, relativity whispers another, and both voices meet in the dark heart of a black hole where neither can fully rule. Carlo Rovelli once reflected, "Inside a black hole, time and space exchange roles. What we know becomes what we no longer understand." Cygnus X1 is not just an object. It is a boundary where our knowledge dissolves like mist in starlight. When I think about this discovery, I imagine a lantern circling an infinitely deep well. The lantern is the bright star, glowing faithfully. Easy to see, easy to love. The well is the black hole, silent, bottomless, impossible to illuminate. And yet the lantern moves with perfect certainty, proving the well's presence even though no eye can ever see its water. We too live with invisible gravities shaping our orbits, forces that pull us, define us, sometimes without light or name. To me, The lesson of Cygnus X1 is both scientific and human. Not everything that exists shines. Not everything that shapes us declares itself. Some truths reveal themselves only by the motion they cause in other things. The way the invisible object guided its companion star, some mysteries cannot be stared into, only inferred from the ripples they leave behind. Cygnus X1 became our first tangible reminder that the universe speaks in many languages: light, shadow, gravity, silence. And in that silence we sometimes find the most honest truths. It taught us that darkness is not emptiness, but architecture, not absence, but presence, not the end of meaning, but the invitation to search more deeply. As we drift through this cosmic tale, let its calm strangeness settle. Let it remind you that wonder requires no brightness, only attention, only patience, only a willingness to listen to the quiet parts of the universe, for it is often in the whispers, not the shouts, that the cosmos reveals who it truly is. In the drifting hush of the universe, where starlight moves like slow breath across an endless sea, there is a region around every black hole that glows with a beauty so violent it borders on sacred. This is the accretion disk, a halo of torn matter swirling in the final choreography before crossing the invisible frontier known as the event horizon. And in this dance of destruction and light, the cosmos reveals one of its most delicate puzzles: an event horizon, mystery that has mesmerized astronomers for decades. Richard Feynman once remarked, "Nature uses only the longest threads to weave her patterns." The accretion disk is one of those threads, weaving gravity, motion, heat, and time itself into a single luminous structure. It forms not because matter wishes to fall, but because it cannot fall straight. Everything in the universe carries memory of its motion, and that memory, angular momentum, must be honored. When a star ventures too close to a black hole, gravity stretches and tears it apart, unraveling it strand by strand. But instead of plunging inward like rain into a well, the scattered debris begins to orbit, is less than, circling in a widening spiral of heat and friction. Leonard Susskind once said, "Black holes are the most perfect absorbers and the most perfect mirrors. Their absorption is unstoppable. But their approach requires a slow negotiation with the laws of motion. Matter first becomes a ring, then a disk, then a storm of ions racing so fast they nearly break the definition of speed. And in that frantic orbit, temperatures rise to almost 10 million Kelvin, hotter than any forge humans could dream of, hotter than the core of most stars. At these temperatures, atoms cannot remain themselves. Electrons are stripped away. Protons collide like sparks in a cosmic grinder. Friction becomes fire, motion becomes light. The disk becomes a beacon around the very thing that emits none. This is why the matter around a black hole radiates X-rays with such startling intensity, as particles slide past each other at a significant fraction of the speed of light. Their collisions are no longer gentle. They are catastrophic, energetic, explosive in microscopic bursts. The heat produced in these interactions releases high-energy photons that scream across the galaxy. We hear them as flickering X-rays, an echo of matter's last resistance before surrendering to gravity. In some galaxies, these disks shine so brightly that they outshine all the stars combined. We call them quasars, cosmic lighthouses visible across billions of light years. Imagine a region smaller than our solar system, yet brighter than an entire galaxy. It is a paradox of scale, a reminder that the universe loves extremes. Martin Rees captured this beautifully. The universe is under no obligation to be sensible to the human mind, and nowhere is this more evident than in a quasar's blazing core. But why doesn't matter simply fall in? Why does this disk persist for millions or hundreds of millions of years, glowing in a slow spiral of inevitability? The answer lies in momentum, the insistence of motion to continue its rhythm. Just as an ice skater, spinning with arms extended, slows and speeds up with movement. Matter orbiting, a black hole must obey the same laws. As it moves inward, it must spin faster. For the universe keeps careful balance. If it cannot spin faster, it cannot go deeper. So the disk forms, not as an accident, but as a necessity of cosmic bookkeeping. This spinning barrier is why falling into a black hole is astonishingly difficult. More difficult than climbing out. Matter must shed its angular momentum, like a dancer slowly discarding layers of costume before reaching center stage. It loses energy through collisions, through heat, through light, and in some cases through jets of plasma that shoot out from the poles like cosmic flames. Only after losing enough of this burden does matter finally slip inward. And that slipping is not quick. It can take millions, even hundreds of millions of years for matter to complete that last surrender. The disk's glow is the chronicle of its long goodbye, a luminous testament to the patience of gravity. When I reflect on accretion disks, I see them not merely as astrophysical structures, but as metaphors for our own struggles. We too circle the things that pull at us, unable to fall straight into change, shedding momentum slowly, painfully, beautifully. Transformation is rarely direct. It spirals, it heats, it brightens before it becomes still. There is a gentle lesson hidden in this cosmic whirlpool. That resistance is natural. That orbiting something does not mean avoiding it. That movement toward the unknown often requires time and friction, and the slow erosion of old motion. The universe teaches us that falling is a process, not an instant. And at the center of it all, the event horizon remains a quiet mystery. A border with no substance, yet infinite meaning. The place where the glow ends and the silence begins. The final threshold in the long spiral of matter and light, in the soft darkness of the universe, where silence feels ancient and space stretches like a slow breath. There is a question that lingers like a low note at the end of a cosmic melody. Can a black hole, the very symbol of inescapable gravity, truly evaporate? This is one of those cosmic existential questions that unsettles even the calmest minds. Not because it is frightening, but because it forces us to rethink what emptiness means. Stephen Hawking once said, "Empty space is not empty, it is filled with temporary particles that pop in and out of existence." In that single sentence lies the seed of Hawking radiation, a phenomenon so delicate that it feels more like poetry than physics. We often imagine the vacuum of space as a clean slate, a perfect nothing. But nature refuses to give us nothing. At every moment, quantum fields ripple beneath the quiet surface of space, humming with subtle energy. These fields fill all of existence, stretching through galaxies, between atoms, through time, through you and me. Even when nothing is present, the fields remain, trembling softly. This trembling gives birth to what physicists call virtual particles, pairs that appear, touch the world, then vanish as if they were never real. Writing that uncertainty is not a limitation of measurement, but a fundamental feature of nature, the quantum fields are allowed to break the rules briefly, creating particles from borrowed energy, as long as they repay the debt by annihilating again almost instantly. A fleeting handshake between existence and non-existence. Then came a remarkable experiment, the Casimir effect, where two metal plates placed close together were pushed inward by invisible pressure. The space between them allowed fewer virtual particles than the space outside. So the imbalance moved the plates. A gentle nudge from particles that shouldn't exist, proving they must. Near a black hole, these pairs behave differently. The enormous curvature of spacetime disrupts the perfect symmetry of creation and destruction. Sometimes one particle of the pair falls inward, trapped forever, while the partner escapes outward as radiation. Roger Penrose once described this region as the edge where geometry becomes destiny. And Hawking realized that this escape of energy must come at a cost. A black hole loses mass whenever one of these particles escapes. It is as if the black hole pays the price of existence for the particle that fled. Mass melts into light, and the darkness grows ever so slightly thinner over unimaginably long timescales. A black hole can evaporate entirely. Small ones vanish faster, large ones more slowly, because the curvature around a tiny black hole is sharper, more violent, more disruptive to the balance of quantum fields. Some doubted Hawking's idea for decades. For how could we ever detect such faint whispers of radiation? But then came a clever path to mimic a black hole, not with gravity, but with sound. Researchers created a sonic black hole by pushing sound waves faster than their speed in a moving fluid, forming a horizon where phonons, the sound equivalent of particles, could not return. And there, at this artificial horizon, Hawking-like radiation was seen, not imagined, not theorized. Seen. A small echo of a grand cosmic truth. When I reflect on Hawking radiation, I feel a strange comfort, a sense that even in the darkest places, the universe breathes out a little light. Not even the titans of gravity. That change touches everything: stars, black holes, atoms, and us. There is a gentle lesson here. What we think of as permanent often dissolves slowly under the quiet workings of time. Even the most unshakable things leak energy, shed weight, transform. The universe teaches us that loss is not an ending, but a natural flow, a movement from one form of being to another. When you stand under the night sky, imagine virtual particles flickering around you. Imagine black holes glowing softly with their final breath. Imagine space-time itself trembling in delicate patterns that keep existence alive. These questions are not just scientific, they are human, they are existential. They are the quiet heartbeats of a universe still learning what it means to exist. In the quiet shimmer of the cosmos, where galaxies drift like lanterns on a dark river, there rises a set of questions so soft, yet so profound, that they unsettle even the most disciplined scientific mind. Questions not about stars or gravity, but about reality itself. When physicists gaze deeply enough into the universe, they eventually find that the boundary between what is real and what is perceived begins to blur, like a horizon dissolving into fog. In that blur lives one of the gentlest yet most powerful mysteries. We have the question of what real truly means. Niels Bohr once whispered, "Everything we call real is made of things that cannot be regarded as real." Few lines in science feel as poetic or as unsettling, because the closer we look at matter, the less solid it becomes. Atoms fade into clouds. Particles dissolve into vibrations. and the substance of the universe melts into a network of fields humming beneath all things. It invites us to ask whether matter, the very thing we touch, hold, build with, is merely a pattern in an invisible fabric. Quantum field theory tells us that every particle, every atom, every piece of matter is nothing more than a localized tremor in a field that stretches across the universe. An electron is a vibration. A quark is a vibration. Even light itself is a vibration. And when vibrations cease, the thing disappears. What remains is the field. Calm again, Frank Wilczek once reflected. The world is a symphony of fields playing a harmony we call reality, and in that harmony, matter is more like music than stone. But if matter is only a vibration, then what is mass? Einstein taught us that mass curves space-time, and space-time tells matter how to move. This intertwined dance blurs cause and effect, leaving us to wonder whether mass is a property of matter or simply a response to the shape of the universe around it. Could mass be only the echo of geometry? A kind of gravitational shadow? John Archibald Wheeler once said, "Matter tells space-time how to curve. Space-time tells matter how to move." But he also hinted that maybe geometry comes first. And matter is just geometry wearing a mask. If the curvature of space-time changed, would mass change as well? The equations suggest it would. The deeper the well of gravity, the heavier things seem. The flatter the geometry, the lighter the world becomes. This invites a quiet, yet profound idea that mass is not fixed, not fundamental, but relational, a soft imprint of space-time rather than a hard property of particles. And if mass is an imprint, what does that make us? Each of us, a temporary gathering of vibrations, held together by geometry, shaped by fields, unfolding moment by moment. It begins to sound as though we are shadows cast by a deeper reality, platonic echoes, holographic projections in a cosmic hall of mirrors. Gerard Hooft once speculated, we might be nothing but the holographic projection of a deeper physical theory. And the more we study black holes, the more this idea feels less like philosophy and more like quiet fact. The holographic principle born from black hole thermodynamics and quantum gravity suggests that everything we experience in 3 dimensions might be encoded on a distant 2-dimensional boundary of the universe. Our bodies, our memories, our world. Possibly nothing more than a shimmering projection of information. If this is true, then reality is not fake, but beautifully composed, an exquisite tapestry woven from the math of space-time. When I reflect on these possibilities, I feel a gentle humility settle over me. It is not frightening to think we are patterns, vibrations, shadows. It is comforting. It means we are part of something continuous, eternal, woven into the structure of the cosmos. We are not separate from the universe. We are its expression. We are the universe noticing itself through the eyes of matter. There is a lesson buried softly in these ideas. That solidity is an illusion. That permanence is a story we tell ourselves. That identity is a temporary arrangement of deeper forces, and that change constant, fluid. Universal is not something to fear, but something to understand. Just as a vibration comes and goes, so do moments. So do versions of ourselves. So does everything we cling to. If reality is a projection, then perhaps our role is not to grasp it tightly, but to experience it fully, to let it flow through us like starlight across the void, to live gently in a universe that is far stranger than our instincts allow, far more beautiful than our senses can capture, and far more interconnected than we often remember. When you gaze into the night sky, consider that everything you see and everything you are is part of a single vibrating field of being. Consider that matter is music, that space is a canvas, that time is a rhythm, and that all of us, from the smallest particle to the largest galaxy, are caught in the same quiet symphony. These questions do not demand answers. They invite wonder, they invite humility, they invite presence. And in that stillness, in that soft contemplation, the universe feels less like a puzzle and more like a companion. In the dim and swirling outskirts of a black hole, where space folds like silk caught in a whirlpool, the universe performs one of its most astonishing dances, a dance so strange that even seasoned physicists pause in quiet awe, wondering how darkness can spin reality itself into motion. This is the region where space-time begins to drag, twist, and whirl faster than even light can flee. A place where the boundaries of motion are rewritten, and where the imagination must exhale slowly just to keep up. Kip Thorne once whispered, "A spinning black hole drags space along with it. It is as though the fabric of the universe itself is being stirred by a cosmic spoon." And in that gentle metaphor lies the heart of this phenomenon, frame dragging. It is not matter moving, but space itself. Space becomes the river, matter becomes the leaf, and light, for all its pride and speed, can only follow the current. When a black hole spins, the geometry around it becomes twisted by its rotation. This rotation pulls nearby space-time along like threads caught in a vortex, creating a region where moving faster than light is not only possible, but unavoidable. This does not break physics, because it is space-time itself that is moving. Einstein taught us that nothing can outrun light within its own local frame, but frames themselves are free to drift apart at extraordinary speeds, like two boats on a vast sea, drifting from one another faster than the waves between them could ever travel. It is in this eerie whirlpool of reality that another revelation unfolds: the Penrose process. Roger Penrose imagined a daring experiment, one that unlocks energy from the spinning black hole, not by mining matter, but by dancing with the geometry around it. He proposed that if an object enters the ergosphere, the region where space itself is dragged along, it can split into two pieces. One piece falls inward, carrying negative energy relative to infinity, while the other escapes outward with more energy than the original object possessed. A cosmic bargain, a perfect theft, a way to convert the rotation of a black hole into usable power, Penrose once wrote. It is possible to extract energy from a black hole by virtue of its rotation. A statement so bold it seemed almost heretical when first proposed. Yet it stands today as one of the most elegant dances between geometry and motion ever conceived. The numbers are astonishing. Through this process, up to 20% of the object's mass can be converted into pure energy. To place that in perspective, nuclear fusion in our Sun converts only about 0.7% of mass into energy. The Penrose process is nearly 30 times more efficient than the heart of a star. It is a kind of cosmic alchemy, a furnace beyond imagination, a power source that makes every human technology feel like a flickering match. Freeman Dyson once remarked, "The energy stored in a rotating black hole is the greatest source of accessible energy in the universe." If humanity could ever tap this well, we would not merely power civilizations. We would reshape destiny. Stars burn out. Planets freeze. But a spinning black hole holds enough rotational energy to illuminate civilizations across billions of years, a reminder that the universe's darkness is not empty, but overflowing with hidden power. When I reflect on this, I feel a strange mixture of humility and hope. Humility because black holes remind us how small we are, how little we grasp about the architecture of existence. Hope because within these dark giants lies a path, however distant, toward energy that could outlast stars, planets, and even the memory of our own sun. There is a soft lesson woven into all of this, that the greatest power often lies not in brightness but in the quiet turning of unseen forces, that what looks like destruction may also be a reservoir of unimaginable potential, and that the universe routinely hides its gifts inside its most terrifying shapes. Black holes are not just endings, but engines, not just devourers, but reservoirs of possibility. They whisper that what seems impossible may simply require a gentler understanding of the rules. When you listen closely, the cosmos feels less like a machine and more like a meditation, a slow turning, a quiet unfolding, a rhythm that invites us not to conquer it, but to understand it. And in that understanding, perhaps to find a new way of living within it. In the deep stillness surrounding a black hole, where light bends like a trembling ribbon and time loosens its grip, there rises a phenomenon so fierce and so elegant that it feels like the universe exhaling fire. Jets, long, narrow, impossibly bright streams of plasma shoot from the poles of certain black holes with a velocity brushing the speed of light. Their existence seems to contradict everything a black hole represents. For how can something known for swallowing all things also become a fountain that casts matter across the cosmos? Subramanian Chandrasekhar once murmured, "The universe is not only queerer than we imagine, it is queerer than we can imagine." Nowhere does this feel more true than in the quiet fury of black hole jets. They are born from the accretion disk, that glowing river of shredded matter spiraling inward. As the plasma churns, magnetic fields twist and tangle, winding tighter and tighter like cosmic springs. When these fields snap into alignment along the rotational axis, they form channels, narrow tunnels threading through space-time. The black hole spins, dragging space with it, forcing charged particles into these magnetic funnels. Inside them, matter is whipped forward like sparks flung from a grinding wheel. Stephen Hawking described it as a storm where space and magnetism conspire. The jets erupt along the poles because that is where magnetic order survives the chaos. Around the equator, turbulence reigns. Matter collides, ionizes, loses itself in the heat. But above and below the disk, the geometry is calmer, the magnetic lines straighter, the path clearer. It is in these quiet corridors that the universe chooses to sculpt its brightest beams. Two jets, perfectly opposite, like the outstretched arms of a cosmic compass. As they travel outward, they do not dim the way starlight dims. They hold their structure across distances that defy comprehension. Some jets stretch millions of light years. Others reach a billion. Like luminous threads sewing galaxies to the dark fabric of intergalactic space, Martin Rees once said, "Jets are nature's most efficient particle accelerators." And their endurance makes this statement feel almost modest. They travel through the vacuum with nearly no friction, and their magnetic scaffolding stabilizes them. preventing the beam from widening or dissolving. But there is another wonder, the directionality of light within them. When a jet points toward us, its brightness intensifies. Magnified by relativistic beaming, the particles rush forward so fast that their emitted light is squeezed ahead of them, like waves piling up in the direction of a speeding boat. To us, the jet becomes a lighthouse beam, sharp, fierce, almost impossible to ignore. But the opposite jet, aimed away from us, fades, thins, vanishes into the dark. Not because it is weaker, but because the universe tilts its light with motion, a dance of perspectives, a reminder that brightness depends on where we stand. When I think of these jets, I cannot help but feel a quiet mixture of awe and intimacy. They show us that even in the strongest gravity well, energy finds a way to escape, that within collapse, there can be release, that the same object capable of swallowing light can also sculpt it. Black holes do not merely consume. They create pathways for matter to travel further than any other force can send it. There is a soft lesson woven into the violence of these beams. Sometimes the greatest pressure, the greatest collapse, the greatest darkness creates unexpected forms of expression. A life pressed inward by its own gravity may still discover a direction to shine outward. A soul burdened by forces it cannot control may still find a channel where light escapes. The universe reminds us that nothing is absolute, not even darkness. Every gravity has its opening. Every collapse has its horizon. Every shadow contains a path where light can emerge. Jets are not merely astrophysical structures. They are metaphors written in plasma across intergalactic distances. They speak to the resilience hidden inside forces we do not yet understand, and to the creativity of a cosmos that balances destruction with radiance. We often imagine black holes as endings, but their jets reveal a different truth. Destruction and creation are threads of the same tapestry. Matter lost to the disk becomes light gained by the universe. Energy consumed becomes energy returned. A cycle as gentle as breath, as fierce as fire, as patient as time. And so, in the quiet hours, when I look at images of these jets stretching like cosmic brushstrokes, I am reminded that the universe is an artist of impossible strokes. It draws with gravity, it sculpts with time, it paints with plasma. And sometimes, in the darkest regions of space-time, it crafts beams that shine longer than civilizations. ChatGPT said, "In the deep quiet of the cosmos, where ancient light drifts toward us from a universe still in its childhood, there rests a paradox so immense that it bends not only space-time but also our intuition. The largest black holes we have ever seen, the true giants of creation, do not live near us. In this older, calmer corner of the cosmos, they live far away, so distant that their light began its journey when galaxies were still forming, when the universe was but a restless adolescent still full of raw fuel. And among them stands Ton 618, a titan weighing 6 billion suns, an object so luminous and so monstrous that it feels like a cosmic exaggeration. Stephen Hawking once said, "The universe has not only a stranger history than we imagine, it has a stranger future than we can imagine." Ton 618 embodies that strangeness. Its existence forces us to ask how something so impossibly large could have formed when the universe was so impossibly young. In those early times, matter was everywhere, dense, unclaimed, swirling through a universe much smaller and hotter than today. Galaxies collided frequently. Gas clouds fell inward without resistance, and young black holes gorged themselves faster than modern ones ever could. The early universe was a feast hall without rules, a place where the seeds of supermassive black holes could grow like wildfires in a dry forest. TON 618 likely began as a massive seed, perhaps the collapse of a giant primordial cloud, or the merger of several early black holes. But more importantly, it formed in an era overflowing with fuel. Hydrogen and helium lay thick in every direction. Dwarf galaxies crashed together like drifting embers. Gas funneled endlessly toward the centers of young galaxies. In such a rich environment, a black hole could grow 1 billion solar masses in under 1 billion years. A growth rate impossible today, closer to us. In this quiet, mature universe, there simply isn't enough matter left to sustain such monsters. Most of the gas has become stars, planets, or has been heated and pushed outward by ancient supernovae. Galactic mergers are rarer. The cosmic pantry is nearly empty compared to those early epochs, and so black holes grow more slowly now, nibbling rather than feasting. This is also why quasars, black holes lit up by blazing accretion disks, are scarce near Earth. A quasar is a furnace powered by torrents of infalling gas, and modern galaxies simply cannot supply that kind of abundance. Our Milky Way contains a black hole of only 4 million solar masses, a quiet beast fed by sparse clouds drifting near the center. Nothing like the torrents that fed early giants. We see the largest black holes far away, not because they live only in the past, but because only their bright quasar phase can be seen across billions of light years. This is the Malmquist bias, the simple truth that the brightest objects dominate our vision while the dim ones fade into silence. A distant quasar blazes like a beacon across time, drawing the gaze of telescopes. But a nearby black hole without a glowing disk is nearly invisible, a quiet shadow among the stars. There is a gentle irony in this. The universe shows us its largest black holes only when they are young, wild, and radiant. But the older ones, perhaps just as massive, sit quietly in galaxies we cannot yet see. Dimmed by age and scarcity, brightness does not always equal size, and silence does not always mean smallness. When I think of TON 618, I imagine a scarlet lantern burning at the beginning of time, a creature formed in chaos, thriving in abundance, growing in ways no modern galaxy could support. It reminds me that growth depends not only on what something is, but on the environment in which it lives. Early black holes were not stronger or hungrier. They simply lived in a universe young enough to feed them. There is a quiet lesson in that vision, that greatness often requires timing, not just strength, that there are seasons of abundance and seasons of scarcity in the cosmos and in our own lives, and that sometimes the brightest things we see are not the closest, but the ones whose light has traveled the farthest to reach us. ChatGPT said, "Where darkness breathes slowly and light drifts like a thought half remembered, there exists a concept so strange that it feels more like a riddle than a reality: the white hole, the mathematical mirror of a black hole. A creature that does not swallow the universe but spills it outward in a single radiant exhalation. Einstein's equations, those delicate threads binding space and time, allow for both. The solutions that describe a black hole, when mirrored in time, naturally give rise to its twin. If a black hole is a place where nothing can escape, then the equations whisper of a counterpart where nothing can enter," John Wheeler once noted. For every black hole solution, there exists a time-reversed twin as bright as its sibling is dark. In mathematics, symmetry is a kind of truth, But the universe does not always honor every truth with existence. A white hole is that symmetry, the outbreath to a black hole's inbreath. Where the black hole gathers, the white hole scatters. Where one absorbs, the other rejects. A white hole would be a region where matter and energy burst outward, unable to ever return. A one-way fountain from the deep fabric of space-time. Nothing could cross its horizon inward is less than any more, but everything inside would spill outwards until nothing remained. Yet this purity is exactly what makes it suspect. The universe is not gentle enough to preserve such perfection. A white hole could not tolerate a single grain of dust. A single photon trying to fall in. Even the smallest disturbance would destabilize it, making it collapse under contradiction. Leonard Susskind once said, "Nature hates boundaries without interaction. The white hole is precisely such a boundary, too clean, too absolute, too untouched. So while the equations embrace it, reality may shrug and walk away. Still, the idea refuses to fade, because even if white holes do not form from stars the way black holes do, they might appear at another moment entirely the end of evaporation. Hawking radiation slowly leaks mass away from a black hole, photon by photon, until one day nothing remains but the imprint of what once was. Some theories suggest that in this final instant, when quantum gravity takes center stage, the collapsing geometry could rebound, turning inside out, releasing whatever information was trapped within, not violently, but in a soft unwinding of space-time. Carlo Rovelli described this possibility as a bounce rather than a burial. If so, a white hole might truly be the final breath of a dying black hole, a brief, fragile, luminous whisper of information returning to the universe. Not because the cosmos must do it, but because symmetry might ask it to. A last gesture of balance, a coda to the long song of collapse. When I think of white holes, I imagine them not as objects but as possibilities, not as certainties, but as reflections. They remind us that reality has shadows in mathematics, echoes that may never be heard yet still shape our understanding. They ask us to hold lightly the boundary between what exists and what could exist, and they whisper a gentle truth that understanding the universe means accepting not only what it reveals, but also what it almost allows. In the quiet depth of the universe, where light bends like a whispered secret and time stretches thin as silk, there exists a possibility so delicate that it feels more like a dream than a destination. The idea that black holes, especially the spinning ones, may not simply be prisons of gravity but gateways, doorways, corridors carved through space-time itself. The notion of wormholes has always hovered between physics and poetry, and yet its roots are firmly planted in Einstein's equations. A spinning black hole, a Kerr black hole, behaves differently from its quieter sibling. A non-rotating black hole curves space-time inward, collapsing everything into a single point of no return. But when it spins, the rotation drags space-time with it, twisting the geometry like a whirlpool twisting water. Frame dragging becomes so intense that inside the rotating structure, the singularity stretches from a point into a ring of infinite density, hollow at its center, a doorway carved open by motion. Roger Penrose once said, "A rotating black hole reveals structures far richer than a static one." And he was speaking of this, the possibility that the mathematics of the Kerr solution naturally unfolds into a tunnel, a wormhole, not simply a hole in space, but a bridge between two regions of space-time, perhaps two corners of our universe, perhaps two universes entirely. In the Kerr geometry, The ring singularity does not necessarily destroy everything that touches it. Instead, the equations describe alternate paths, trajectories that slip through the ring, bypassing obliteration, emerging somewhere new, somewhere else. It is a strange kindness offered by a region otherwise known only for its hunger, and so the question naturally arises, could one travel through such a wormhole? Could a spacecraft is less than number, or even a single photon, cross that shimmering throat and emerge into a different part of the cosmos, a different epoch, a different universe entirely? Carl Sagan once reflected, "Wormholes are an irresistible idea, passages through space and time that offer a shortcut to distant stars." Yet he also knew that reality is not always kind to irresistible ideas. The wormholes given by the Kerr solution are mathematical doors. But they are not stable ones. They tremble at the slightest touch. Even a single particle entering the throat injects energy into the geometry, and that energy collapses the passage instantly. The tunnel pinches off, sealing itself. Often before anything fully enters, the equations permit the doorway, but physics refuses to leave it open. Kip Thorne described this fragility with a gentle truth. Wormholes are gravitationally unstable. They must be held open by forms of matter we do not know how to produce. Exotic matter, negative energy, pressures that defy our intuition, all would be required to keep the tunnel from closing. Without them, even light would fail to pass. The universe creates the possibility, but not the practicality. Yet the idea lingers, because wormholes remind us that the structure of space-time is far more fluid than we once believed. They reveal that geometry is not fixed, that time is not rigid, that space is not simply a stage but a living fabric capable of folding, bending, touching itself in places far apart. When I think of wormholes, I do not picture highways through the cosmos. I picture questions, soft, luminous, unsettling. Questions about connection, unity, and the deeper architecture of existence. They remind us that the universe may be stitched together in ways we cannot yet perceive, that the distance between two stars may not always be as large as it seems. That separation may be an illusion carved by our limited senses, and in a more personal way, they hold a lesson that not all gateways are meant to be passed through. Some exist to widen our imagination, not our reach. Some doors are meant to be seen, not opened, and some mysteries exist not to be solved, but to remind us how vast our unknowing truly is. Wormholes are one such mystery, shimmering possibilities sewn into the mathematics of space-time, fragile as dreams, luminous as hope, and humbling as the night sky. ChatGPT said, "In the soft hush of the cosmic night, where the universe breathes in slow currents and the stars shimmer like ancient memories, there exists a family of ideas so gentle yet so daring that they read like poetry written in the language of mathematics. Loop quantum gravity and the vision of a big bounce are among these quiet rebellions, attempts to stitch together the quantum grain of space-time with the sweeping curvature of gravity. And from this stitching emerges a possibility almost mythic in its beauty, that black holes may not simply end in silence, that the universe itself may not have begun in a single explosion, but in a return. Carlo Rovelli once wrote, "The world is not continuous, it is woven from loops of quantum threads." In that image lies the heart of loop quantum gravity, the idea that space-time is not smooth but granular, that beneath the vast velvet of the cosmos lives a tapestry of tiny vibrating loops. These loops limit how tightly space can be squeezed, preventing infinities and giving rise to something unexpected. A black hole collapsing into a singularity may not collapse forever. Instead, when the density reaches the limit set by these quantum threads, the collapse rebounds. Space-time pushes back. What was falling inward is thrown outward again. A black hole's death may not be a vanishing, but a transformation. Some physicists imagine that the final whisper of a black hole, the moment after Hawking radiation has stripped it to its last quantum breath, could be a tiny white hole, a speck no larger than a grain of dust, yet carrying within it the encoded memory of what once fell inside. The information that seemed lost, scattered, erased by the long darkness, might then leak back into the universe in a soft unwinding, not as matter, but as structure, as pattern, as a quiet correction to the cosmic ledger. It is a gentle vision that nothing is truly lost, not even in the jaws of a black hole. Lee Smolin once reflected, "In quantum gravity, information is not destroyed, it is transformed." If this is true, then every black hole is a doorway not to oblivion, but to renewal. Every collapse holds within it the seeds of release. And then comes the grandest question of all: if black holes bounce, could the universe itself bounce? Loop quantum cosmology suggests yes. In this view, the Big Bang was not the beginning of everything, but the end of something before it. The moment when a previous universe collapsed, reached the limit of quantum density, and rebounded outward in a new expansion. Our cosmos could be the echo of an older cosmos, the child of a universe that lived, breathed, collapsed, and gave birth again. This idea turns the familiar picture of the cosmos into a cycle: expansion, contraction, bounce, renewal. There is no singular beginning, only transitions, no creation from nothing, only transformations across cosmic ages. The Big Bang becomes the dawn of a new world, not the birth of existence itself. It is a story as old as myth and as modern as quantum theory. The phoenix that burns and rises again, the tide that recedes only to return, the breath that exhales, inhales, and flows without end. When I reflect on the Big Bounce, I find a strange comfort. It suggests that cycles define not only stars and galaxies, but the entire universe. That endings are never absolute. That collapse carries within it the seeds of expansion. That the universe is not a single miracle, but a repeating one. There is a quiet personal lesson here, that when we reach the limit of our own collapse, when life squeezes us into our smallest form, we too may find a way to rebound, to unfold, to begin again, as the universe does, as black holes might, as existence has done countless times across cosmic memory. Loop quantum gravity invites us to see the universe not as a straight line, but as a rhythm, a cosmic heartbeat, a cycle older than matter itself, and perhaps, within that rhythm, we may find our own. In the quiet hours of the night, when the mind drifts gently between waking and dreaming, the universe begins to ask questions that do not belong to physics alone, questions that rise like distant echoes, soft yet impossibly deep, brushing the edges of our understanding. A video about black holes cannot help but wander into these realms. For black holes are not merely objects, they are invitations. Invitations to wonder what existence truly means, and what place we hold in the architecture of the cosmos. The first question seems simple at a glance: do we truly exist? Not in the everyday sense, but in the fundamental sense. Quantum mechanics tells us that matter is not as solid as it appears, that particles blur into fields, that the self is a pattern, a momentary arrangement of vibrating possibilities. Niels Bohr once said, "Everything we call real is made of things that cannot be regarded as real." And from that gentle paradox blooms an unsettling thought. Perhaps existence is more fluid than we imagine. Perhaps we are waves in a deeper ocean, passing shapes in a larger pattern. Then comes time, that steady river we trust with our memories. Einstein taught us that time is not absolute, not universal, not the same for all who drift through it. Stretches near speed, and in the heart of a black hole, may even stop. If time is a landscape rather than a flow, what does that make our lives? Moments may coexist, futures may already be written, and the straight line we call life may be a curve we simply walk slowly. Carlo Rovelli whispered, "There is no single now, the world is a network of events." Why do these ideas feel foreign to intuition? Because intuition evolved to navigate stones and sunlight, not space-time and singularities. Our senses are tuned to the middle world, not the microscopic dance of quantum fields, nor the titanic gravity of collapsed stars. The universe does not bend itself to human understanding. We bend ourselves toward it. Every discovery is a stretch, a widening, a humbling. The strange is not strange to the cosmos, only to us. So we ask, could black holes be gateways for humanity's future, not merely tunnels or engines, but opportunities to see the universe in a way we never have? They stretch time. They twist geometry. They store information in ways we barely grasp. Some physicists dream of harnessing their energy, navigating their gravity, learning from their horizons. Perhaps one day, these dark giants will not be the end of light, but the beginning of new knowledge, a doorway not to escape, but to understanding. And then the gentlest question of all, will the universe repeat itself? Is our cosmos a single note, or a melody that loops through eternity? Some models suggest an endless cycle of expansion and collapse, birth and rebirth, like the breathing of a cosmic lung. Others see a single unfolding from nothing to everything, ending in silence. Yet even these answers feel like metaphors, for the universe rarely grants simple truths. Herman Whale wrote, "The world is a four-dimensional closed melody, and perhaps that melody repeats sweeter each time." When I sit with these questions, I do not search for certainty. I let them move like constellations across the mind. They remind me that existence is fragile, that time is flexible, that understanding is a horizon we never fully reach. They remind me that the universe is not a machine to be solved, but a story to be listened to, a story told in light and darkness, in gravity and waves, in questions that deepen the longer we hold them. Because perhaps reality is not about answers, perhaps reality is the act of wondering itself. In the quiet glow at the end of our long journey together, I want to take a moment to simply breathe with you and reflect on the vastness we've wandered through. Tonight we have drifted past the edges of stars, touched the shadows of black holes, traced the trembling threads of quantum fields, and listened to the universe whisper questions older than time itself. And through every mystery, every horizon, every paradox, every cosmic wonder, you were here, watching, listening, thinking, dreaming. Your presence turns these distant stories into something warm and human. So thank you, truly, for giving your attention to a universe that rarely fits inside language. Thank you for letting curiosity guide you, for choosing to spend your time exploring ideas that stretch the mind and soothe the soul. Thank you for your patience as we drifted through slow orbits of thought, wandered into strange corners of space-time, and allowed the cosmos to unfold at its own gentle pace. I hope this journey left you with more wonder than answers, more calm than confusion, more awe than certainty, because that is the nature of the universe, not to hand us conclusions, but to offer horizons, not to close our curiosity, but to awaken it. And I hope that somewhere in these stories, you felt a little more connected to the stars above, to the world around you, and to the quiet mysteries inside your own mind. As we close this chapter, know that your presence truly matters here. Your curiosity keeps this channel alive. Your questions guide where we travel next, and your support allows these cosmic journeys to continue. So from the heart, thank you for being part of this endless exploration, and wherever you are listening from, may the universe surround you with peace, wonder, and the gentle feeling of belonging to something beautifully vast.